Hello again. Here we are considering other bases for logarithms. We looked at ln, the natural logarithm, in the previous videos. But now other bases. ln was based on e because its inverse function is e to the x, and the base of that function is e. Here, that is called a natural logarithm. Log, Log, is called common logarithm, and the base for that is 10. So log of x is the inverse function of 10 to the x. We can generalize this to any base. For example, log base 2. For that, we have the inverse function of that to be 2 to the x. And these are the relationships between exponential and logarithmic function pairs. In general, we write this as log base b. So if you have log of v in base b equals w, that is equivalent to the base b raised to w equal to v. And if you remember from exponential function, the base cannot be negative and cannot equal 1. So those are the restrictions on the base. And it's the same base we're using for logarithms. Let's look at a property called the change of base formula. Any log of any argument in any base can be written as a ratio of two logs with the same base. I mean, the ones that are standard are natural log and common log, which your calculators have buttons for. And any base can be written as a ratio of these two logs. In theory, this is equal to any base log over the same base log of the same ratio. So here's an example. 3 to the x equals 5. We want to solve for x. We want to find x. My pen, all right. All right, so here x is equal to, because we're using log base, we're using exponential base 3, so now that this translates to log base 3. So we have log base 3 of the output of the exponential here is 5. That becomes the input for the corresponding logarithmic function. So x is log 5 in base 3. We can also write it in the as a natural log, as a ratio of two natural log by using the change of base formula, the formula above right here. So this is we can say, or x equals ln of 5 divided by ln of 3. We can use common log as well. So here's another example. We have e to the 2x minus 1 equals 4, and we want to solve for x. So we know that that exponent, 2x minus 1, can be written as ln, which is log base e. The base of the log should match the base of the exponential function. Only then, when the bases match, these are inverse functions. So this would be ln of 4. So the output of the exponential function, which is 4, becomes the input of the logarithmic function. In this case, is ln base e. Now, to solve for x, you don't need to put this in a calculator. There is no exact value. in decimal form. Keep it as ln of 4. Add 1 and then divide by 2. And that would be the exact answer. So x is 1 plus ln of 4 divided by 2. So here's another example. Log base 2 of x equals -1. We want to find x. So we know x has to equal the base 2 raised to that -1, which is the output of the log. It becomes the input of the function 2 to the x. Again, because 2 to the x and log base 2 are inverse functions of one another. So x equals half. Here's another example. Log of 3 in base x equals 2. This time the base is the unknown. And we can, again, change this to the exponential function. So we can write x, the base. The exponent would be 2. And that is equal to 3. So 3 is the output of the exponential function, as well as the input of the logarithmic function. And that's how you relate the exponentials to logarithmic of the same base. So now we can solve for x. And we know x has to be positive, because it's the base of the log, okay? And x cannot equal 1, okay? So those are the restrictions for the base. So here, when you take the square root of both sides, you get x equals plus or minus 3, but x equal to minus 3 is not acceptable. So therefore, x equals 3 is the answer to that problem. Here's another example. We have log of 1/9 in base 3 equals x, and we're finding x. So again, we can solve this by changing to the corresponding exponential form. The base is 3, the exponent is x, the exponent is the output of the log, and that should equal to the input of the log. So the output of the exponential function should match the input of the log function. The output of the log function should match the input of the exponential function. But this one we can easily solve by writing 1/9 as a power of 3. 9 is 3 squared, but it's in the denominator, so this is 3 to the -2. 1/9 is 3 to the -2. So that when the bases match and you have two exponentials equal, the exponents obviously have to be equal as well. So x has to equal -2. Here's another question. These two we can write as an exponential equation. 1/6 raised to the x equals 36. Now 36 is 6 squared. 1/6 is 6 to the -1. If we match the bases, then we can set the exponents equal. So 1/6 I'm going to write as 6 to the power -1, and that is raised to the x. And 36 I'm writing as 6 squared. Now, by using one of the rules of exponents, 6 to the -1 raised to the x, the rule of exponent requires multiplying those two. So the left is 6 to the -x, and the right is 6 to the 2. And that gives you -x equals 2 Therefore, x equals -2. So that's the answer to this equation. Here's another problem. E to the ln of 5. We know ln and e to the x are inverse functions of one another. Here we are inputting 5 into the ln, and the output of that is going into e. So e would undo everything ln did. And in fact, if you look or if you watch the first video in this lesson, you can see this is one of the properties of log and exponential. So the left side is just 5, and that's equal to x. So x equals 5 is the answer here. And here's another example. Now this one is the opposite of the other. You see 4 to the x is exponential, and log base 4 is the inverse of that. So x goes into that exponential function, and the output of that is going to the log function, and log would undo everything the exponential did because the bases match. So the left is just x. You can also see this in the first video in this lesson. So x equals 3x minus 1, and now we can solve for x. So I'm subtracting x and adding 1, so 1 equals 2x, so x equals half. And this concludes the video.